Welcome back. Hey, I got a story to tell you. So Chicky Chick and I, we're kind of best buds here. Chicky Chick's been, Professor Chicky Chick, I should say, has been assisting me for a number of videos, if you may have noticed. And we were telling jokes, and she's like, hey, I got a joke for you. What do you get when you cross the enolate of an ester with a nucleophilic acyl substitution? And I gotta be honest with you. She lost me at enolate ester, and so I was like, I don't know. She's like, a beta keto ester! And then she just started cheeping hysterically and rolling all over the floor. And I'm like, oh, I'm sorry, I have no idea what you're talking about. And then she's like, you're gonna have to write the mechanism. I'm not gonna just tell you. So here I am. Assigned a mechanism trying to figure out what this beta keto ester thing's all about. So you can see here in our example, we've got two of the same ester. We have methyl acetate and methyl acetate. And in 2 steps, we're going to do something with those esters. We're going to take sodium methoxide in the first step, and then we're going to have some acid, some H3O+, and then we're going to get this molecule here, okay? And actually, now that I look at it more closely, maybe I kind of understand what she's talking about. So I got an ester here, and I've got an alpha carbon and a beta carbon, and this beta carbon has a carbonyl, so it's like a ketone here. So I can kind of sort of see the beta keto ester thing going on here. So I'm going to show the mechanism of this reaction. And I also want to talk a little bit about these 2 items here, because it's actually kind of important that we have this particular base. Like, I can't get away. This base has to be matched up with this ester. And so I'm going to talk about why that is a little bit. Hopefully not too much. I may not have enough time to do that. And then it's also important that we have this acid here. So let's look at the mechanism of this reaction. You may notice the lighting's a little different and that you don't see a bright spot right there. So I'm actually going to erase this because I don't think I need it. I'm like, I've graduated to like my brown belt in videography here. Okay. All right, so let's look at this lighting's actually, I got to give credit where it's due. It's courtesy of my wife. She found this lamp in the closet, and so we may have solved some of my lighting problems. Okay. All right, so let's see if I can pull this mechanism off here. Okay. All right, so there's methyl acetate, and what we're gonna do, remember the sodium's a spectator, so I'm gonna take my base here, and I'm gonna pull off this alpha carbon here, or alpha hydrogen. Okay, and that's a proton transfer. And I think a lot of this is, I'm better keep myself out of trouble here. It's under equilibrium, and really the equilibrium, a lot of these equilibria favor the reactant. Okay, so we make this enolate. Okay, and what that enolate is going to do, remember we've got a couple resonance forms. Gotta think about what I'm drawing here. All right, there's the other ester. Okay. So we're gonna take our nucleophile, and we're gonna swing around here, like so. I don't know if you can see that. And do this, which is called a nucleophilic addition. Probably the ugliest nucleophilic addition I've drawn in a while, but oh well. All right. And so what that does is we make a new carbon-carbon bond, which I'm going to put in green here. Okay, this OCH3 group I'm going to put down here. And I got an oxygen up here. Okay. And then what's going to happen next is, you might recall from our previous chapter that these would often leave as a leaving group. Okay, and so that's exactly what's going to happen here. We're going to have a nucleophile elimination. This lighting's good as long as I don't stand in front of the light. There, how's that? I guess it's okay either way. Great. And so once we do that nucleophile elimination, we get to this. Ooh, I dropped something. Can you see what I dropped? Something got forgotten along the way. An oxygen. Okay, that oxygen's still there. Get my lone pairs here, so I'm gonna put that there. Okay, that's a bond. And then okay, so we get to there. There's my alpha beta keto ester. Okay, so there's my product. So this Claisen condensation, we call it, has a proton transfer, nucleophilic addition, and then a nucleophile elimination. And so these last two steps, nucleophile addition, nucleophile elimination, together we call them a nucleophilic acyl substitution. Okay? Now, let's talk about a couple things that I said were important. All right, so one thing that's really important is that this base, sodium methoxide, matches up with the ester. Note that I have a methyl ester. The reason that's important is, as all this is going on, okay, equilibrium arrows, okay, simultaneous to that, you might have remembered a reaction called transesterification that we saw in the previous chapter. And so what transesterification is we're swapping out this methoxy group with whatever our base is, okay? So you can imagine if I had ethoxide here instead of methoxide, I would be getting a mixture of things going on. Like I'd have the methyl ester, but I'd also be creating the ethyl ester in solution. And so then I would get a mixture of products where some of them had a methyl group here and some of them had an ethyl group. And we don't usually want a mixture of products, okay? And we also would not use sodium hydroxide here because sodium hydroxide saponifies esters. It turns them into soap, okay? Especially, well, if it's got a really long chain, it would be soap. And we're not trying to do that either right now. So, okay, so that's the first consideration. That explains why I'm using sodium methoxide. If this was an ethyl ester, I'd use sodium ethoxide. Okay. The other thing I have to consider is now these hydrogens are more acidic than what I started with. Okay, so here they have a pKa of about 24. Okay, now these hydrogens are between two carbonyls, so if I deprotonate this, it has a lot of resonance stabilization. So this is more acidic. It has a pKa equal to 11. Okay. The significance of that is this doesn't really stop here, okay? And I'm gonna have to erase a couple things and keep going around the board. Okay, so I'm gonna have another molecule of sodium methoxide. Okay. And it's gonna deprotonate this. Okay, and this is a very favorable equilibrium because methanol has a pKa of about 16, 15, 16, and this has a pKa of 11. So it's gonna favor this side of the equilibrium. And that's ultimately what drives this whole process, because up to this point it's unfavorable. Okay, and so that gives us this enolate plus methanol. Okay, and then this is why we throw in H3O plus at this point, because now we didn't really want the enolate, we wanted the neutral form of this. Okay. Whoop. Okay. So we've got a proton transfer here, and then we've got another proton transfer. Okay. So really, this whole mechanism goes to here before we add the H3O plus. But I would, if I ask you to draw a Claisen condensation, I'll probably ask you to get to this point. Because this is the same as that. It's just, it's going to go to here, and then we add H3O plus to get it back. I know that's a little confusing. All right. Let me show you one other example here. So I want to show you one that's in line notation. Okay. If I have time, I have to stay under 15 minutes here. Okay. So let's take this ester. It's an ethyl ester, and I'm going to say there's two of them. Okay. Because I'm doing an ethyl ester, I got to be careful. I'm going to use sodium ethoxide, not sodium methoxide, and then I'm going to have a second step with H3O plus. All right. To draw the product, I'm going to take one of the esters. I'm going to remember that we make the enolate, okay, and that is going to attack the second ester. We have two of these, and we're going to form a bond to here, and then the ethoxide is going to leave. 1, 2, 3, 4. So we're going to get this product plus ethanol. Okay. So you can kind of see here, maybe if I number these, 1, 2, 3, 4. We got 1, 2, 3, 4, and then 1, 2, 3, 4. So we're forming a bond between carbon 2 of one of the esters and carbon 1 of the other ester. Okay, and I better stop here because I'm running fast out of time, and YouTube's not gonna like that. So thanks for watching.